Hello math students, topic 16. This is on second order linear inhomogeneous ODEs. Notice that was also the topic for the last topic, topic 15. And this time we're going to learn how to solve an inhomogeneous second order linear differential equation using another method known as the variation of parameters. And this method would also be applicable to when the coefficients of the y prime and the y are also non-constant. So consider a second order linear inhomogeneous ODE with or without constant coefficients. So the coefficient p of t and the coefficient q of t might have t's involved. Notice I still have, though, a coefficient of 1 in front of the y double prime. Now suppose that y1 and y2 are linearly independent solutions to the corresponding homogeneous ODE. So imagine that we have a 0 here instead of a non-zero expression. And if we have two linearly independent solutions to this differential equation, when this is a 0 on the other side, then we can use them to construct a particular solution to this inhomogeneous ODE. And we can do so by using the following formula. And this looks quite complicated. There's a lot of pieces here, but there's some symmetry that you can see here as well. This formula is called the variation of parameters formula, and I do not intend to discuss how it came about. Feel free to look up in the text or watch videos on the creation of this formula. Instead, I would just encourage you to write this on your note card when you are doing an examination so that you can just look it up. Now this formula only helps you get the particular solution y sub g, which is not the general solution. So we'll see how to, once we know y sub g, we can use that combined with a linear combination of y1 and y2 to create the general solution. So that's still the same as it was before. This is just giving us a new way to find this particular solution y sub g, depending on what the forcing function is over here, g of t. Now if the coefficients, reading right here, if the coefficients of the ODE are constant, so the p and the q are constant, then y1 and y2 can be found from the characteristic equation, much like we've already done in this class. If the coefficients are not constant, then you would need a different method to find y1 and y2, or in the case of what you'll see in the homework, they will be provided. In fact, that's what's going to happen right here in this first example. Let's start with this homogeneous second order linear differential equation. Notice that it has a coefficient of t, not a coefficient of 1. So we could divide that t by, the entire equation here by t, so that we have a y double prime being 1 as in this general form, leading to this formula. We'll do that in a moment, but right now all I want to do is have you show that these two functions, y1 and y2, are in fact linearly independent solutions to this homogeneous, and it's homogeneous because there's a 0 on the other side, to show that they are linearly independent solutions to this homogeneous ODE right here. And we can do that with or without dividing by this t to get a 1 in front of the y double prime. Okay, let's begin with y1. y1 is e to the 3t. So y1 prime will be 3e to the 3t. And y1 double prime will be 9e to the 3t. We're going to substitute these into this differential equation. Let's move that over a little bit. Into this differential equation and see that the differential equation is satisfied. So the differential equation reads that t times y double prime, so 9e to the 3t, minus, parentheses, 3t plus 1. I gotta make sure I give myself enough room here to do both of these solutions, so I'm going to zoom in a little bit here, shrink that down slightly. So minus 3t plus 1 times y prime. Y prime was 3e to the 3t, and then plus 3y. And y was just e to the 3t. And we want to show that this will in fact be 0. We'll see what we get when we notice that we can factor out an e to the 3t from all of this. So that gives me just a 9t to start, minus, and then here we need to distribute this 3 and this negative. But I'm going to factor out the exponential. So we get minus 9t minus 3. And we have a plus 3 over there, and exponential has been factored out. And as you can see, the 9t's are going to cancel, and the 3's are going to cancel. So we get a 0 in the end, and that shows that this function, we move these where they are slightly, I'll put them column, that this function y1, which is e to the 3t, does in fact satisfy this differential equation. Okay, now let's verify the other one. Okay, y2. y2 is equal to 3t plus 1. So y2 prime is just 3, and y2 double prime is 0. So this should be fairly straightforward to verify. So we have t times, now I'm just going to plug these functions into this differential equation. So we have t times y double prime, so t times 0, minus parentheses 3t plus 1 times y prime, which is 3, and then plus 3 times y. And I'm going to give myself a little more space here, move this stuff over slightly, zoom in a little bit. Oops. There we go. Plus 3 times y, and y was 3t plus 1. And we want to show that that this will become 0. Well, this part here is already 0. That's t times 0. I'm going to distribute this negative and distribute this 3. So we have minus 9t minus 3. And then I'm going to distribute this 3 right here across those parentheses and get 9t plus 3. And notice that, once again, everything cancels out. We get 0. Therefore, y2 is also a solution. So y1 and y2 are both solutions to the differential equation. And are they linearly independent? Most obviously, yes. There is no way to multiply either one of these two functions to make it be the other, at least by a constant. All right. y1 cannot be expressed as a constant times y2, and y2 cannot be expressed as a constant times y1, so they are linearly independent. Check. We should probably make mention of that officially. So y1 is not equal to some constant times y2. So that makes it makes the two solutions linearly independent. And there are also solutions to the ODE. Now we're not going to talk about how to find these solutions to this second order homogeneous differential equation with non-constant coefficients. That's going to be something we just don't discuss in this class. But if we do know them, how can we use them to find a particular solution when we have an inhomogeneous version of this differential equation, which is exactly what we have right here. So on this slide here, we're going to use the variation of parameters to find a particular solution to the inhomogeneous ODE below. Now it's inhomogeneous because we have a non-zero forcing function over here on the right. Then give the general solution. Okay, the first thing we want to do is identify what two linearly independent solutions would be if this was homogeneous. Make the forcing function be 0 and find or be given two linearly independent solutions. Now we've already demonstrated that these are linearly independent solutions, so we already have that done. They were provided to us. 3t plus 1 are linearly independent solutions to the homogeneous ODE. I'll just abbreviate that. Okay, so that's done. Now, these would also be linearly independent solutions even if I were to divide both sides by t. So the next thing I would want to do is get this differential equation into this form, which means that we need a 1 coefficient in front of the y double prime. That's the only thing that's not consistent with our form. So I'm going to divide everything by t to begin. So we get y double prime minus 3t plus 1 all over a t times y prime plus 3 over a t times y is equal to, now t squared divided by t will just become t and then e to the 3t. So we've tweaked this differential equation by dividing everything by t, and we have this one here, which now matches the form that we want. And we can still show that these two solutions are solutions to the homogeneous version of this ODE. So if I change this right here back to 0, I could still show that these are solutions to that different homogeneous differential equation. Okay, so back up to here. So if we have a second order linear inhomogeneous ODE with a forcing function of g of t, and we happen to have two linearly independent solutions to the homogeneous version, which we do, then we're going to use this formula here to find a particular solution. Now notice the symmetry. The denominators are identical. That's one thing to keep in mind. The positioning of the y1 and y2s flip-flop. And then both of them have the g forcing function. And the one that's subtraction is the y1, is the one that has the y1 here that's not differentiated. So whatever function you put right here in this position should be the function that's in this position, which is the one that's subtraction. And then the other one, so if we have one function here, the first function in this denominator, it's not differentiated, so y sub 1, the opposite one goes there, and this is the positive term. So this isn't too hard of a formula to memorize. There's a few things that make it simple to memorize, and we are going to apply it now to find y sub g. Y sub g is equal to an integral, is equal to y sub 2. Y sub 2 is 3t plus 1 times the integral of y sub 1, which is e to the 3t, times the forcing function. Now keep in mind the forcing function is not t squared e to the 3t. We had to get a 1 here first, if you recall. So we had to divide by t first. This is our forcing function. This is our g of t. So multiplied by g, so times t e to the 3t. And then divide by, and let's see, this was, we're going to start with y sub 1. Y sub 1 is e to the 3t times the derivative of y sub 2, which is just 3, minus the derivative of y sub 1, which is 3e to the 3t times y sub 2, which is 3t plus 1. So that is our denominator. And then we have dt. And then minus. And now we flip-flop. We put the denominator, the next denominator will be the same, but we're going to put the function y sub 1 as the coefficient of the integral. So there's y sub 1 times the integral of y sub 2, which is 3t plus 1, times the forcing function, which is t e to the 3t, all over, and then the same denominator as before. So once you think about that correctly and do it correctly, you don't need to rethink it, just copy and paste it. dt. So we got to be able to complete these two integrals to find y sub g. This is one, sometimes these integrals are not doable by hand. And so this is where the variation of parameters formula might fail us. It all depends on whether we can A, find y1 and y2 in the first place, and B, carry out these integrals. If we can't do either of those things, then this formula won't be helpful for us. So let's see now if we can actually complete both of these integrals. There's going to be lots of simplifying that's going to occur. And if you look at the denominators, you could factor out an e to the 3t from both denominators. That's going to cancel with an e to the 3t up above. Let's see what happens when we do this. Y sub g is equal to, so we have 3t plus 1 times the integral, and I'm going to go ahead and do the factoring and the canceling. So really what's going to happen is this e to the 3t is going to cancel with that one and that one. They're gone. And over here, this e to the 3t is going to cancel with both those. Now let's see what's left. We have t e to the 3t over, and the bottom just becomes, we do have a negative 3 that needs to distribute across those parentheses. So we have a 3 minus 9t minus 3. And the 3's are going to cancel. That'll be nice. And the t's will then cancel after that. Even nicer. And the second integral, coefficient e to the 3t times the integral of, and we have the same denominator, but our numerator is 3t plus 1 times t over, and then this same 3 minus 9t minus 3. And then dt. Okay, from here, we have 3t plus 1. This integral is going to just become, well, we're going to get 3 minus 3 in the denominator, so it's going to be, and the t's will cancel, so there will be a negative 1/9. So I have to integrate e to the 3t over negative 9. That's going to be e to the 3t over, divided by another 3, negative 27. I did a few steps there for time's sake, or for space's sake. And the next one, we're going to get a negative 9t in the denominator. Right? Let's go ahead and show this cancellation of these things. And then the t's are gone, and then the t's are gone. So we get a negative, I'm going to just bring out that negative 1/9 right now, make this positive and put that over a 9. And we really just had to integrate next 3t plus 1, which is 3t squared halves plus t. And don't worry about the plus c's. Leave the constants of integration off to construct your y sub g, to construct your particular solution. Okay, from here we want to do some factoring and simplifying as much as we can. And notice that there's an e to the 3t present in both of these, so I'm going to factor that out of the entire expression. So we get y sub g is equal to e to the 3t times, and then get a common denominator. I'm looking at what that common denominator might be, or maybe I can do that later. Let me just distribute the negative 1/27. So we get negative t9ths minus 1/27. And then over here, I'm going to distribute they see the e to the 3t was factored out, so I'm going to distribute the 1/9 across these parentheses. That gives me plus t squared over 6 plus t9ths. Okay. And notice, oh, this is convenient. The t9ths, negative t9ths and positive t9ths cancel, leaving us t squared over 6, and this becomes our particular solution. So y sub g is equal to e to the 3t times t squared over 6 minus 1/27. Okay, that's the particular solution. I would leave it to you to take the time to show that this function here will be a solution to this inhomogeneous second order with non-constant coefficients ODE. But now we want to construct the general solution. So the general solution is y is equal to, we begin with the particular solution y sub g, which is e to the 3t times t squared over 6 minus 1/27, plus an arbitrary constant times the first of our two linearly independent solutions to the homogeneous version, so times plus a constant c1 times e to the 3t. And let me give myself, again, a little bit of space here. And then plus an arbitrary constant times the second solution to the homogeneous version, so 3t plus 1. And there's our general solution. All right, the next slide. Use the variation of parameters formula to find a particular solution to the ODE below, then give the general solution. Okay, so the first thing, this time the y sub 1 and y sub 2 are not given to us, but also we're back to the realm of having constant coefficients, which means characteristic polynomial can be used to find our y1, y2. And let's make that a 0 here first. Characteristic polynomial to the homogeneous. If I'm looking at the homogeneous version of this, then I want to solve this differential equation. Characteristic polynomial would be lambda squared plus 4 is equal to 0. This would give me lambda is equal to plus or minus 2i. So that means my y sub 1 will be cosine 2t, and y sub 2 will be sine 2t. So So we just use the characteristic polynomial and characteristic equation, which is right here, and its roots to determine your y sub 1, y sub 2. Okay, now that that's done, we can make sure that your coefficient of y double prime is 1, which it is. So this is our g of t this time. So g of t is secant of 2t. That's our forcing function. And now we can go straight to the formula. So the characteristic, or the particular solution, y sub g is equal to y sub 2. Y sub 2 is sine 2t times the integral of y sub 1, which is cosine 2t, times g, which is secant 2t, all over. And now we do y sub 1 times y sub 2 prime. So y sub 1 is cosine 2t, and y sub 2 prime is 2 cosine 2t. So we get 2 cosine squared 2t. And then minus. Now we do y sub 1 prime times y sub 2. And y sub 1 prime is negative 2 sine 2t. I'm looking at this one right here and differentiating it. We get negative 2 sine 2t times sine 2t. So we get minus negative 2 sine squared 2t. Okay. This is what you get when you're looking at these two functions, y1, y2, and then you do this calculation for your denominator. And then minus. Now we have y sub 1, or sorry, minus y, yes, y sub 1. Y sub 1 goes at the next coefficient, which is cosine 2t, times the integral of, now we do y sub 2, which is sine 2t, times the forcing function, which is secant 2t. And then our denominator is the same. So once you get this done correctly, you just copy paste. Okay, let's see where we go with this. The denominators. Let's focus on those denominators. We can factor these 2's out. That leaves cosine squared of an angle plus sine squared of the same angle. So we can use the Pythagorean identity on that, and that just makes it 2. All of this here collapses to a nice clean 2. So that's going to happen there as well. That's convenient. So I'm going to factor that 2 out. So we have a 1/2 sine 2t times the integral of, and then cosine 2t times secant 2t. Well, secant's 1 over cosine 2t, so they just cancel. You get a 1 here. So in the end, all we have is just a 1 that's left over, dt. That's extremely convenient. Minus, I'm going to factor out that orange 2 as well, so we just have a 1/2 cosine 2t times the integral. Now, sine of 2t times secant. Well, secant's 1 over cosine, so we get sine over cosine, which is just tangent. So we have the integral of tangent 2t that needs to be done here. And the question is this a doable integral? And if we know how to integrate tangent 2t, then we can finish this. Therefore, it seems like our variation of parameters formula will see us through to the end. Both of the integrals in the formula are doable by hand. Let's see, let's keep going. The integral of 1 is just going to be t, so we have essentially t halves now. Sine 2t is our first part. Then minus 1/2 cosine 2t. Now, what is the antiderivative of tangent 2t? So let's do a little quick brainstorm. If you remember the integral of tangent x dx, this is a natural log secant of x. Is one way to say this antiderivative. And if this becomes a 2t instead, or a 2t and this becomes a t, then we're going to have a 2t here, but to reverse chain rule, we're going to have to multiply our answer by a half to counter the chain rule. You could do a formal u substitution here to do this, but with enough practice, we can just give an answer here. It's going to be 1/2 natural log of the secant of 2t. Okay, so our y of g in the end becomes t halves times sine 2t minus 1/4 times the cosine of 2t times the natural log of the absolute value of the secant of 2t. Now I'm going to copy paste this, because to form our general solution, we begin with our particular solution, and then to that we're going to add a constant times y sub 1. Y sub 1 is cosine of 2t, and then plus a constant times y sub 2, which is sine 2t. And this gives us the general solution that we are after. Okay, let's just do one more slide. Previously, we used the method of undetermined coefficients to show that y sub g equals 2 times e to the negative 3t is a particular solution to the ODE below. So this is something that we've done in a previous lecture. We're going to confirm this now by using the variation of parameters formula instead. So this is just to show you that in some cases we have multiple ways of attacking these problems, because this is a second order linear differential equation with constant coefficients. And the other side of this was a function form for which we could use the method of undetermined coefficients. And when we did that, we got this answer right here. But now we're going to do this a second way, and use the variation of parameters formula to get the answer. So we still need to consider the homogeneous version of this to find out my y1 and y2. So if this is the homogeneous version, change the forcing function to 0. And also I should point out that the coefficient of y double prime is already a 1, so this is our g of t. Just be clear about that. That's the g of t we're going to be using in our formula. And next, the characteristic polynomial. Lambda squared plus 3 lambda plus 2 is equal to 0. This does factor to lambda plus 2 times lambda plus 1. So we get different real lambdas, negative 2 and negative 1. So my y1 is going to be e to the negative, in no particular order. Let's just pick an order. It doesn't really matter which one we say is first. Let's say it's the e to the negative t is y1, and y2 is going to be e to the negative 2t. Right? E to the lambda t and e to the lambda t. Okay, now we're ready to set up our variation of parameters formula to get our y sub g. Y sub g is going to be y sub 2, which is e to the negative 2t, times an integral of y sub 1, which is e to the negative t, times our forcing function, which is 4e to the negative 3t. All over, and then the denominator. We're going to start with a y1, which is e to the negative t, times y2 prime, which is negative 2e to the negative 2t, minus y2, which is e to the negative 2t, times y1 prime, which is negative e to the negative t, and then dt. So there's our denominator. We make this division line go a little bit longer. So there's our first integral, and then we need to subtract and effectively just now switch these two functions. So we have e to the negative t, which is our y sub 1, times the integral of e to the negative 2t, which is y sub 2, times the g function, 4e to the negative 3t, times the forcing function. And then the rest of this is going to be the same. So I'm just going to copy and paste that. Okay, now let's focus on these denominators and see if we can simplify them. Let's see, the e to the negative 2t times e to the negative t is going to be e to the negative 3t. And we're going to have negative 2 plus 1. So we're going to have negative 1 e to the negative 3t is what both of these become. So let me do this in a couple steps here. So I don't want to do too much in one step. It gets confusing. E to the negative 3t integral. The top is e to the negative t times 4e to the negative 3t. And the bottom just became negative e to the negative 3t. And then that's also true for the other integral. Became negative e to the negative 3t. All right, now we can do the cancellation. E to the negative 3t, e to the negative 3t, gone, gone, gone. So some things simplify nicely here for us. This negative here and that 4, I'll factor them out. So we have y sub g is equal to negative 4. The coefficient is e to the negative 3t. And then we're doing simply an integral of just e to the negative t dt. Minus. Now over here I'm going to do the same thing. I'm going to take the negative and the 4 out. So this will actually become plus 4 e to the negative t times the integral of e to the negative 2t dt. Okay, so we've got to do both those integrals. Y sub g is equal to, the first integral, the antiderivative of e to the negative t is itself divided by 1. So we get e to the negative t divided by negative 1, plus, and then the next one, 4e to the negative t, and then the integral of e to the negative 2t is itself divided by negative 2. So these, we get e to the negative, double checking my work here, e to the negative t. I feel like I made a copy error, and I did. This 3, I don't know why that became, I had 3 on the brain, but that should have been a 2 in the front, right? I just made a copy error, so I'm glad I caught that. Change those back to 2s. And so we're going to multiply these e's, and we get e to the negative 3t, and another e to the negative 3t. And here we get positive 4, and this will become a minus 2. So positive 4 minus 2, so we get 2e to the 3t, negative 3t. And that confirmed what we got when we did this using the method of undetermined coefficients. You may want to look back on your notes and see how we did it the other time. And that's all we were expected to do for this. It did not say construct the general solution, but let's go ahead and just do it anyway. The general solution would be the 2e to the negative 3t, the particular solution, plus some constant, c1, times the first homogeneous solution, which is e to the negative t, plus some constant times y2, the second homogeneous linearly independent solution. And here is our general solution. So let's put a check next to here, so we confirmed that we got the same particular solution, and then of course here is our now general solution. And we'd go back to a new particular solution if this had some initial conditions, like y sub 0 equals something and y prime of 0 equals something. Then I'd have to then find the two c's, the c1 and c2, to get the particular solution that also satisfies the initial data. But that was not asked of us here. And this wraps up topic 16, which is showing this new method for determining the general solution of an inhomogeneous, linear, second-order, ordinary differential equation, and potentially with non-constant coefficients.